Hello, my name is Joseph Schroeder, and I'm one of the authors on our paper, Quantifying Postural Instability with Pose Estimation Software and 3D Depth Extraction. And today I'm going to be sharing a brief little bit about our work and findings. All right, so to start with, the origin of this paper really resides in a desire to better quantify postural instability, which is an important risk factor in a variety of disorders, notably Parkinson's. The current standard for determining how bad a patient's postural instability is the retropulsion test, in which a clinician pulls on the shoulder of a patient and then observes their response to that stimulus. There remains an issue, however, on how to standardize this test. For example, is the clinician pulling with the same force every time? Particularly, how do you determine what's a good or bad score? A number of steps, step lengths, step quality, all of these things could be quantified. And there's a necessity to quantify them both in clinic and outside of a research setting without the need of expensive and detailed equipment. And so that's sort of the purpose of this. And we, for our study, we looked at Deep Lab Cut for that, which is a open source program that uses deep learning to label points from videos. And so then a challenge comes up with that, in which in cases like our study, where you're using just one video frame, you don't have multiple perspectives. So you only have 2D data that's in the pixel plane. And you've got to take that data from 2D to 3D, which we do in MATLAB. And we use the pseudo inverse, which actually utilizes the forward process going from 3D to 2D, which has the forward mapping matrix, a 3x4 matrix that you can see there at equation 1, that consists of both the camera's intrinsic properties and the camera's relative location, or the extrinsic matrix. And that data can be taken then when using the pseudo inverse from the forward mapping matrix and force a 3D unique solution. And this is done by having 3 points that we know the distances between and can then get that forward mapping matrix from it. This data can then be taken into Excel, post-process, and this, in theory, since it's such a low barrier to entry on cost, just requiring a camera, could be taken to at-home monitoring tools, which is pretty promising for a lot of studies. And so what the results look like, for our study, you've got the raw data from MATLAB there, and you can see this is just in the anterior-posterior plane. That was the only plane looked at for this study. It's fairly clean. There's a little bit of noise, some outliers, but in general, it's pretty clean, and a lot of those outliers can be contributed just to low confidence points, which Deep Lab Cut labels as points that essentially it couldn't see or they were out of frame during that time. And so once you post-process it, you can look at the validations that we have there. The first one, a subject stepped to a specific line, and if they stepped on the line, they give a thumbs up, stepped off it, thumbs down. And those results are there, and they weren't super clear. So we did a second validation in which they stepped varying step lengths and recorded each of those, which are shown in the y-axis, and the DLC outputted lengths are in the x-axis. And as you can see, those lines are pretty good. It's fairly low variance. In addition, they had slopes around 1.015 and 1.044, both of them showing a lot of promise for being pretty close to accurate to the exact results. And so in the future, taking this to a lot of other studies would be really the desirable goal. It's a low barrier of entry and can be applied retrospectively, like we're doing currently on our Parkinson study for postural instability. And further automation can be applied even to reduce the amount of user input and streamline the process. So thank you for your time, and I hope you found this presentation interesting, and feel free to check out our paper for more information.